Alright, so Chapter 3, Section 3, logarithmic functions are the inverse of the exponential functions. Taking a look at these notes, I do see that we were doing some logs before. Maybe we should have been doing them, but of course we did it in Algebra 2. So either way, we'll go over more of the specifics of logs in this set of notes in the assignment. And see what we can remember. So in the previous assignments, if you had graphed them and found where they met or did some guess and check, that was totally legitimate. Alright, so just to review, an inverse function flips over the y equals x line, or x equals y. So it goes up 1 over 1. Wow, that is rotated. And so the idea is that the reflection would, and this is where it's kind of hard, that one is there, it goes like this. Alright, so, goes over the axis there. So it's actually here. There we go. Wow, that took a little bit. Of course, you can also flip x and y in order to get there. So, for instance, this coordinate right here would have been 0, 1, and so its inverse would have flipped x and y, so 1, 0, which is there. Alright, so that's your inverses, anyway. So we have our log functions, and the inverse of as the inverse of exponential functions. And here's what we call exponential form. So you've got your base raised to a y value equals an x, or what we call the answer. And then in order to write that in logarithmic form, base b, whatever that base happens to be, you take the exponent and it's now equal log base b, and then it's of the x. So that's that idea of being able to switch between one and the other. Why do we do inverses? We do inverses with the base that's already existing because it turns out that log base b of b cancels, and so y equals y. We also have b raised to the log b power canceling, and so because of that, y equals y. Of course it does. Alright, so here we are looking at logarithmic format, and there are two basic formats, and so that's where our base is 10 or our base is e. And so even though it doesn't say a little 10 down here, there is technically a 10 there. If there is any other value that's there, that means that you would have to put whatever that number is. And we did do a few problems in the previous assignment where the base was like 1.117 or something crazy. So just kind of looking at that. This one here technically has a tiny little e there, which would mean that it's a base. And this is also, at least the way that I started writing them, wow, cursive. You write it with like a cursive L, because we are talking about natural log. There are a lot of people that think that says in instead of LN. So natural log with an N and an L. So either way, we use E because of things like being able to continuously grow versus at a regimented pace or time. So when we talk about transformations, it can happen for a function, and if we take that function and want to move it left or right, that function is going to have something done to the x value inside of the equation. So if we want to go right, for instance, we would have an x minus a number, and if we want to go left, we would have x plus a number. If we want a vertical or horizontal stretch, that is where we're going to have a number out front. So we've got this a value out front multiplied by f of x. And if that a value is greater than 1, we're talking about a vertical stretch. And actually, if we just talk about the absolute value of a, so that we can talk about negatives as well. And then if we talk about a being between 0 and 1, meaning fraction in air quotes, that's going to be a vertical compression. And of course, if we add the absolute values, that means that anything that's like a negative fraction will also vertically compress. And then we also have if a is negative. And I guess that's where they're talking about it here. So if a is negative, we have a reflection across the x-axis. I think I just put way too many C's in across. And then if we have a negative b value, which is actually the thing that's inside, so for instance, if we have a negative inside with this x, that means we're going to flip across or reflect across the y-axis. Alright, and then your translations up or down is nice, because all it does is tack on a number afterwards, which would move it up, or tack on a number afterwards, subtracting, which would move it down. And you can always see if one of these works, because you can just graph each of them, the parent function and then the one with the difference in it, so that you can kind of tell. Alright, so here we are with some properties, just to make sure that we know what's happening here. We kind of already did this one and this one, where we said those cancel, and so that's why x equals x. The only other one here is that this one is like saying, so if we rewrite it, b to the 0 equals 1, and so hopefully we remember that anything raised to a 0 power does in fact equal 1. And then this last one, if we rewrite it, means that b to the 1 equals b, which of course it does, because b to the power of 1 is itself again. Moving on with a few more practice problems here. We're going to see if we can do these, of course, without a calculator, just to kind of see if we remember the basics. So taking a look at this one, and again, sometimes, well, pretty much every time they're written in log to evaluate, it's helpful if you write it in exponential format. So if I rewrite log base 4 of 4 in exponential format, and this is something you'll want to do in your assignment as well, it helps if you say that it equals something, so in this case an x. And so to rewrite, we take 4, bring it to that x, and it's going to equal 4. And all we need to do is find out what would be in this piece here, because that would mean that x and that piece are the same. And so the only thing that's going to make 4 to the x equal to 4 to the 1 would be an x of 1. Again, if you do this in your calculator, log base 4 of 4, you're in the math key, and scrolling down to where it says log, and then you get to insert a base. The next one, log base 7 of 1 equals a number, so we rewrite in exponential format to realize that it's 7 to the x, and we want to know when will that equal 1. And so the only way that 7 to something is going to equal 1 is if x is 0. Alright, now we get to apply a few more pieces. So rewriting this next one here, we actually have 10 to the x. And when does that equal? Oh, I'm ignoring that this is a tiny little 10 here, and then it's of this 10 to the negative 4. So 10 to the x, when does that equal 10 to the negative 4? And of course that's when x equals negative 4, because they're in the same spot. The next one has the same piece. There's a log base 10, so that 10 log 10 cancels. And so we're just left with 14. Alright, the next ones get a little bit trickier, but this is our base of 5. So we're asking 5 to the x is going to equal the third root of 25. So what you want to do is make this thing so that it has a base of 5 so that you can compare. So we make that thing a base of 5 by rewriting 25 as 5 squared. And then hopefully you remember that anytime you have a root, that's actually the denominator of the power fraction. So we could rewrite this as 5 to the x equals 5 to the 2/3, and therefore x is 2/3. Lots of power remembering there. And then the last piece here is saying 3 to the x equals 27. So 3 to what power equals 27? Well, 27 is 3 to the 3rd. So x equals 3. Moving on, natural log functions of common base e. So again, e is here even though it doesn't seem like it is, but when you have the natural log sitting there, e is officially your base. So if we rewrite e to the 0, e is just like 2.7 something. It's found in your second division key. So e to the 0 is 1. Anything to the 0. This one here is your canceling. So it's saying natural log of e to the natural log of e is just 1, because e to the 1 is going to equal e, and so what is that piece that's there? The next one, natural log base e of e, cancels as we've seen before, and so y equals y. And then the last one, e to the natural log of e, either way tells you that x is x. Alright, then we'll try to evaluate the following here. Again, it helps me at least if I write base e so I know that that's there. So this first one here, if we write it equal to x, it's e to the x equals square root of e. So hopefully we remember that square root means there's a 2 there. E without a power means it has a 1. And so technically this 2 becomes the denominator of e. So e to the x is going to equal e to the 1/2. And so x is a half. You can also, again, just type this into your calculator the way it is, and you'd get a half, but we definitely want to know why. Then the next piece, e natural log of e is going to cancel. Oh, and so I don't think that's supposed to be there. And so 4 is our answer. And then same thing here, natural log of e to the e tells us that 5 is our power. The last piece here is graphing log of x, and that's going to be the inverse, and then shifting it. So notice that this one here is plus 3, so it's going to eventually mean that we're going up 3. X minus 3 would mean that we're going to end up going right 3 if it's inside. 3 log x is going to mean that we stretch vertically by 3. And then a negative log of the original parent function is going to mean that we flip over the x-axis. So, graphing our original function, we have 0.1, negative 2, so basically 0. Oh, these are x's, sorry. So, 0.1, x, negative 2, 0.1, 1, 1, 0, over 10, up 1, 1, 2, 3, 4, 5, I think that's 10. Alright, and so we have this as our original parent function, having an asymptote at x equals 0. And then if we want it to shift up 3, that means that this piece that maybe was at 1, 0 is now going to be up 3, but still have the same asymptote. The next one that moves right 3 is going to, let's see, right 3, have this intersection. And a new asymptote. The next one after that is going to stretch vertically by 3. So really doesn't end up doing a whole lot. But if you want to think of it in terms of this actual function here, if we have the k of x here as the y values, we would multiply that by 3. So -6, for instance, -3, 0, 3, and 6. So if we graph them, 1, 0 is still there, but then -1, oh sorry, 0.1, -3. And then, let's see, so over 10 up 3. So hopefully you can see that it kind of, from the original black equation, stretches it vertically a little bit. It's a little hard to tell on a 10 by 10 grid. And then the last one flips it over the x-axis, which is the horizontal one, and so we just do a mirror image like I was trying to do earlier. But the x equals 0 or y-axis is still the asymptote. Alright, so that's a lot of fun colors happening. And then we have an assignment that kind of goes over all of our exponential rules and logs.